Hi everyone. In this video, I'll try and give the talk I would be giving in person at EGU in Vienna. My name's Ollie and I'm with Fathom in the University of Bristol, and I'll be discussing some work I've done in collaboration with colleagues near and far. This work focuses on stochastic flood modelling. How we can ensure the floods we simulate over large scales have a realistic spatial structure. It can be quite a dense and inaccessible topic, so I'll do my best to outline the core concepts in a short space of time. Typical large-scale flood models generally do not represent spatial dependence, shown on the left-hand side of this schematic here. They simulate the same return period flood everywhere simultaneously. This obviously doesn't represent a real plausible flood event, and so the losses arising from, say, a 100-year flood everywhere are not truly a 100-year event. Such a phenomenon is incredibly less likely than one in 100 years, and depending on the scale we're working at, physically impossible. This means the probability loss curve will misestimate risk in the tails. A flood model accounting for spatial dependence, on the right-hand side of the figure, simulates plausible flood events, and our understanding of what may be impacted at a single point in time aids us in calculating tail risk more accurately. Generally speaking, there are two ways to represent spatial dependence in large-scale flood modeling. Both have advantages and disadvantages. The more brute force method is a continuous hydrological simulation, where a long time series of synthetic rainfall is routed through a runoff model and cascaded into a hydraulic model to understand impacts. Such a method is advantageous since it captures the full event hydrograph, but continuous simulations are incredibly computationally expensive, meaning model components have to be heavily simplified to make the model practicable. You can preserve important features of the model, such as high resolution simulation or accurate hydraulic equations, via statistical modeling. This is where you characterize the correlation of extreme flows between locations and then simulate only the extreme events. This is something we've done in the United States in previous work, where we use river gauges to characterize flood spatial dependence across the whole country. An example of this is shown here, where we have our downstream river gauge in red. A closer gauge upstream in yellow, we can see is highly correlated to the red gauge in the scatter plots. The graph plots simultaneously observed river flows in blue, and the statistical model characterizes this correlation so we can extend the period of record with many more synthetic flow co-occurrences in red. The more distant upstream site, in purple, appears less correlated to our downstream red gauge. We can see that given our downstream site is extreme, the upstream purple gauge may not always be concurrently in high flow. One disadvantage of this approach that inhibits our ability to build stochastic flood models globally is the reliance on river gauges, which are not available at a suitable density for this purpose outside of parts of the US and Europe. The question we want to tackle then is whether simulated discharge hindcasts by global hydrological models may be able to supplant discharge observations in a statistical modeling framework. To see if this is the case, we have taken three global hydrological models: CAMOFLOOD from the University of Tokyo, PCR GLOBWOOD from the University of Utrecht, and GLOFAST from the JRC and ECMWF, and look at how well they capture the spatial dependence of flooding in the US compared to our previous gauge-based approach. As an example of the kind of things we've been analyzing, we've got our downstream site on the Missouri River at the green cross and circle, and our upstream tributary is Salt Creek at the orange cross. The top time series shows the modeled flows at these two sites, this time by PCR GLOBWOOD, and at the bottom we have the observed flows. If you look at the y-axis, you can see that these deviate quite substantially. The dashed horizontal lines represent the 5-year flow exceedance at each site, calculated specific to each input data source, gauge or model, with the crosses illustrating where in chronological time the 5-year flow is exceeded in history. We see a fairly poor replication of event chronology too by the model. Some phantom events are simulated which did not occur in the observational record, and some observed events are missed. However, if we count the number of times Salt Creek in orange exceeds the 5-year flow, and then count the number of times the Missouri in green exceeds its 5-year flow simultaneously, both the model and gauge agree the proportion is 50%. Given Salt Creek is extreme, there's a 50% chance the Missouri is also extreme. In spite of all the errors in the model, it arrives at the same conclusion as the gauges when examining correlation. We can input these data into a statistical model. We can translate observed flow co-occurrences in blue into many more plausible synthetic co-occurrences in red, in line with the observed correlation structure. The top two graphs are plotted on the same axes this time, and you can see although there are heavy biases in the model, the general correlation is much the same. If we convert these flows to their quantiles, we ignore the absolute flow volumes and just consider their relative frequencies, as we have done in the two bottom graphs, we can see that the synthetic events based on the model and the gauges are very similar. So this is something we've examined for thousands of stream gauges across the United States. An analysis of site-to-site correlation similarity in this context is pretty new as far as I'm aware, so we've had to devise some new metrics with which to characterize this specific type of model skill. We term it co-occurrence rate error. This is the proportion of times a neighbor is extreme when your site of interest is also extreme. In this talk, our definition of extreme is exceeding the 5-year flow magnitude. In our paper, we vary this definition to see how the results change with different levels of event rarity, but for simplicity here, we just look at the 5-year. So for example, our site of interest here, the blue star, is where we're trying to characterize co-occurrence rates. The shades of red are co-occurrence rates as a percentage at the neighbors. Darker shades of red indicate higher correlations. These are the gauge-based co-occurrence rates, and then these are the model-based co-occurrence rates. And then if we subtract the two, we get a load of errors. We can summarize these errors in a number of ways. Firstly, let's just plot them together. It's a little hard to visualize these millions of different co-occurrences where we see the correlation errors of every gauge versus every gauge, as most data points are concentrated at the very low co-occurrence rates. If we plot these quantiles of model versus gauge co-occurrence rates, we can see these closely follow normal quantiles. We have an unbiased model. Perhaps what's more useful though, is to bin these co-occurrence rate values to ensure that roughly the right number of locations are experiencing broadly similar correlation strengths. You're probably less bothered about a 5 percentage point error with observed co-occurrence rate of 50% and a model one of 55%, compared to if you had an observed co-occurrence rate of 1% and a modeled one of 6%. So we group these values into fairly subjective bins that broadly reflect the density of co-occurrence rates that we see. On the left is a perfect model that doesn't exist. If the bar reaches 100%, it means the same number of locations are simulated within that co-occurrence bin as the gauges. The color of the bar illustrates the local level errors. It shows you the proportion of sites modeled within each bin, which are also sites the gauges placed within that bin. The bar height itself may be a result of too few locations being simulated correctly within a bin, but it's topped up to 100% by the misestimation of other locations. The perfect model then not only has the same number of sites experiencing, say, less than 2% co-occurrence, but also exactly agrees on which sites these are. If we look at the right-hand figure then, we have the results for camouflage once again. We can see that the bars are all pretty close to 100%. Perhaps too many sites have less than 2% correlation, and too few have more than 10% correlation, indicating events are a little bit too localized with respect to observations. Generally, the highest and lowest modeled correlation bins are made up of locations that also fall within those bins according to the observations. The lightest gray occupies most of the first bar, the darkest gray occupies most of the last bar. The sort of middling correlations between 2 and 10% appear to consist of a fairly even mix of locations with a variety of observed co-occurrence rates. Positive and negative biases help the height of the bar reach 100%. The same number of locations fall within that bin as the observations, but it's made up of different locations. Now in the paper, we looked at a whole host of other metrics, which I shan't bore you with now. The final test that we think is the most important is how does this affect your large-scale views of risk? We use the synthetic event sets produced by both the gauges and the global hydrological models to sample from our existing static flood hazard data in the US from our 2017 paper. Events are defined in terms of their return period in each river catchment, and this informs a cookie cutting extraction procedure from the inundation maps to produce the event depths. We can then calculate the damages to buildings in the US arising from these flood events and see how these compare depending on whether the events were driven by models or by gauges. The uncertainty bounds are characterized by the uncertainty and vulnerability relating to the depth damage functions used, which are based on some work we published earlier this year in Nature Communications. We can see that, for example, where our events are defined by using the GLOFAST model, our nationwide view of risk is no different to if we used river gauges instead. To wrap things up then, we cannot rely on river gauges to inform our view of global flood spatial dependence. We will ultimately have to use hydrological models for this. While it's relatively well understood that their simulated discharges are often poor, we find that the relative flow exceedances transpire to produce flood events that are similar to those of river gauges. Crucially, when we compare gauge-based and model-based views of risk using a state-of-the-art catastrophe model, we find the two are virtually indistinguishable. Moving forward then, these results suggest scientifically valid global CAT models may no longer be a distant aspiration, but we do need to test further in other world regions. Thank you.